quick lecture here on conductors, insulators, and semiconductors, and the three methods of charging. You can read through this slide as easily as I can. The key thing to remember about a conductor, which involves mostly metals, are good conductors, is that charge flows easily. It doesn't mean it flows with zero resistance. We'll get into resistance in the next unit, but it flows very easily. And it's all about the electrons in that outer shell. Do you remember the vocabulary word from chemistry, valence shell? That's where things take place. There's a conduction band, and it gets pretty complicated, but it's those outer electrons that are important for electricity and heat. This picture represents that if you place a charge on a conductor, it will spread out evenly around or on the surface of that conductor. Insulators, charge doesn't flow easily. Doesn't mean charge doesn't flow. True or false question on the exam might be true or false. Charge does not flow in an insulator. That's false. It doesn't flow easily. It's millions and millions and sometimes even millions of times less, but it's still some charge will flow. Things like glass, plastic, and rubber. And this picture is supposed to represent that if you place a charge on an insulator, given enough time, it will spread out, but for long periods of time, very long periods of time even, that charge can remain localized. Semiconductors fall in the middle. Silicon and germanium are two most common ones, and the neat thing about this is that you can manipulate whether it's a conductor or an insulator. You can change its conduction properties, and that's amazing. And that's the basis of a little device called a semiconductor, which is like a switch, but with no moving parts, and you can make them microscopic. And that's the basis of the modern electronics world. Moving on. There are three ways to charge objects. The first one is charge by friction, which literally means what it says. You're going to rub two materials together, and electrons are going to transfer from one to the other. You do work to separate the charges, and that work comes from you or whatever else is rubbing the two materials together. This chart over here simply tells you which way the electrons move. If, for example, I was to rub rabbit fur together with wood, electrons would move from the fur to the wood, making the wood negative and the rabbit fur positive. What if we rubbed glass with wool? Well, the electrons travel down in the direction of the arrow, and if you remove electrons, that makes this object positive, and if you add electrons, that's going to make the wool negative. Let's do one more. How about aluminum and silver? Electrons move from the aluminum to the silver, making the silver negative, making the aluminum positive. And that means you're conducting electrons into the silver. If you have silver fillings in your mouth and your teeth and you chew on aluminum, you'll transfer electrons from the aluminum into those silver fillings, into the nerves in your teeth, and right into your brain, which sends a little bolt of electricity through your jaw. If you have silver fillings, or if your parents have silver fillings, ask them to chew on some foil and watch the reaction. Good stuff. All right, finally, we want to make sure you understand that you wind up with equal and opposite charges. Why? Because it's a one-to-one transfer. For every one electron you remove from aluminum, it's going to the silver. Equal and opposite. Method number 2 for charging is charge by contact. This is when the two objects simply touch. You don't have to rub them together, they just have to make contact. Electrons will transfer from one to the other. Why would electrons transfer anyway? Because electrons are always repelling each other. Think of Coulomb's law. There's no place in the universe that two electrons do not repel each other. So if you put a bunch of extra electrons on an object, they'll try to get off as quickly as possible, or whenever the opportunity presents itself. So you wind up with two objects of the same charge. Let's take a look at this 4-panel cartoon here. So right now in this picture they're not charged, and let's just say that she's the one who slides over. The two materials rubbing together would charge her by friction, and let's just say for argument's sake she winds up with a negative charge. These are negative charges, electrons. And then when they make contact, those electrons, which don't all want to be compacted together on her, will transfer. So we'll get an electron transfer from one object to the other. And that's that little spark when you reach out and touch the doorknob, or you scuff your feet across the carpet and you get that little spark. And this spark doesn't come from love. No, this spark comes from simple physics. Albert Einstein was quoted as saying, gravity has no effect on people falling in love. Alright, so that's charge by contact. It's not friction because you don't have to rub the two materials together. Let's take a look at this bottom example. One object has a charge of -4 microcoulombs, and the other object has a charge of +10 microcoulombs. I'm leaving off the micro. If the total charge on both of these spheres is +6. So if they touch and separate, and if they are identical objects, then they will wind up with identical charges, +3 and +3, which still gives us a total of 6 microcoulombs. Now, if they're not identical, the charges will not necessarily be equal. Okay? You do wind up with the same charge on both objects, but not necessarily equal. And that's simply because the objects might not be equal. These two people will both be negative, they'll both have some extra electrons on them, but they might not have the same amount, same number of electrons. And finally, for this lecture, let's take a look at our third method of charging, charge by induction. Charge by induction involves no friction and no touching, at least not between the two objects being charged. Before we can do charge by induction, we need to cover two vocab terms. Number one is grounding. Grounding means you're providing a path for electrons to move literally into the ground. And in this picture in the upper right corner here are two grounds that you would find in your house. Turns out, for safety reasons, that third prong on your outlet in your house needs to be grounded, literally connected to the ground. And we'll talk more about household circuits in the next unit and why this is important. But for now, let's just understand that that provides a pathway for electrons to literally go into the ground. And sometimes there's a wire in your basement attached to the cold water pipe, and the electrons can travel to that pipe, and then that pipe literally somewhere outside your house runs into the ground, and those electrons can get even further away. It provides a safe path in case there's a short circuit. Again, we'll talk more about that in the next unit. For our purposes, electrons, it's possible for us that electrons can also come from the ground to an object. So for us, the ground is a two-way street, and we really don't care which way it works. Grounding will often return an object to a neutral state, and that's important. So for right now, when you see the word grounding, you can think of, oh, it's going to be neutral after I ground it, or I'm providing a pathway for electrons to move to the ground, leaving behind maybe a charge. All right, let's go on to polarization. Polarization is charge separation. Now, in order to have a charge separation, you do need a charged object. So in order to separate the charges on this object here, the sphere, we do need to bring another charged object near it. In this case, we're using the example of a negatively charged object coming near this neutral sphere. And what happens to electrons in this neutral sphere, especially if it's a conductor and charges can move easily? Well, electrons from these atoms over on this side are going to run, not literally, but they're going to move or migrate toward this side, simply because they don't want to be near this negative charge. Like charges repel. These positives doesn't mean the protons move towards the negative charge. Protons can't move in the nucleus. But these are positive nuclei left behind by these electrons that ran away. So we have a charge separation. Look, right down the middle. We've got a positive half and a negative half. We'd say that this object right here is polarized. It's still neutral. Notice that it's still paired up positive and negative. So overall it's neutral, but because of this separation of charges we say it's polarized. When you ground an object in the polarized state, you can charge the object, or it will have a net charge in the end. So if I polarize an object and then I place my finger on this negative side, and that's what you're seeing here in this picture, these electrons can run away into the ground. The electrons, which were crowded on this side of the sphere, once I touch that and provide a pathway to ground, those electrons can now go down into the ground and get even further away from each other. And what's left behind here? A positive object. So when I remove my finger, I'll have a positive object that was charged by a negative object. These two objects never rubbed together. In fact, they never made physical contact between the two. So because this only came close, we needed to call it another name. We called it charge by induction. And that's what this is. In charge by induction, you wind up with two objects with opposite charge. Check question. What method gives you objects with opposite charges? If you're thinking friction and induction, you're correct. In charge by contact, you wind up with two objects with the same charge. Not necessarily equal, but the same sign charge. And that's it for this short little lecture. Thanks for watching.